Okay then, so let's continue with the next part of the video. So we are looking here at the delay definitions first. Okay, so we are looking at the propagation delay of the inverter. Okay, so we have the V in here, V in, and we have the V out simulation. And as we apply V in against time, as we apply V in at 50%, going up to the output going down at 50%, we call that TPHL, or the high to low propagation delay. So not to confuse yourself, when you say TPHL, high to low, it means that the high to low of the output, not the input. So as you can see, it's a high to low on the output. Okay, so TPHL is a high to low on the output, not on the input, which means that on the input we give from low to high. Okay, and we measure at 50%. And then we also have the definition of the fall time. The fall time also, we are looking at the output waveform. So the fall time is looking at the 90% of VDD and 10% of VDD. Between that is your fall time, and of course you have your rise time, and then you have the TPLH. Okay, low to high on the output. Okay, not on the input. And of course you can have the average delay, or the effective propagation delay of the logic gate is just the average of the high to low and low to high. Okay, the Miller effect, I think for me it's not quite interesting. I think I'm going to skip this. It's not really useful for now. Okay, so this one is more interesting. So we're looking at the extrinsic capacitance. So remember, we discussed quite in detail on the capacitance on the previous chapter. So here basically we're going to expand the analysis. So here, what is extrinsic capacitance, or the fan out? So the extrinsic or the fan out capacitance is the total gate capacitance of the loading gates M3 and M4. So what is M3 and M4? We're going to see that. Given by this equation, that C fan out equals to C gate of the NMOS plus the C gate of the PMOS. Given by these equations, we already seen in the previous chapter something similar. So let's look at what is M3 and M4 in this case. Okay, so we have the physical layup of a chained two chain inverters. So M1, M2 is here. So here is your M1, down here is your M2, and then M3, M4. So if you are not familiar with this, let's just go through it quickly. Let's see. Okay, so let's go through the M3 and M4. So basically what happened here is, this is your polysilicon gate. Okay, just a basic on the, because maybe not everybody is have taken VLSI design maybe in the undergraduate. So let's go through this. Some of you have taken, maybe familiar what's going on here. So this is your gate, and here is your source of S1, and this is your drain of 1, drain of 2, and source of 2. Okay, NMOS, PMOS up here. Okay, NMOS, PMOS. Okay, so so what happened here is, we want to see actually the capacitance. Now, because we have the dimension, we know what is the size of the diffusion layers, we know the size of the gates. So here is your L, 0.25 micron. Okay, and here is your W, and it's given by this W and L. Okay, and also given by the table here. Okay, W and L. And what is the WL of your NMOS? So here is your L, and here is your W. Okay, that's the size. So this is what the designer controls. How big you want to design your transistors. Okay, your W and your L. So that one you can control, and we've analyzed already. The sizes will impact your VTC, will impact your noise margins, will impact your speed, and basically it's a parameter, the main parameters that we as designers we can control. Okay, so how do we control it? Just by different drawing, bigger size drawing. We're going to extract it into a spice netlist, for example, and then the spice netlist will show that the dimension according to our drawing. So here, for example, is showing that the area of the drain 0.3. So what is the area of the drain? NMOS. So NMOS area of the drain. So what is the drain? So the drain of the NMOS is here. Okay. So this is metal contact. Okay. So here is your area of the drain, and here is your area of the source. Okay, so area of the source actually just up to there. Okay, so area of the drain equals to area of the source. Okay, and perimeter. So perimeter of the drain. Remember, you have the LS and LD. Okay, and the W. Okay, so we have these parameters. So that's our basically our back-to-back inverter. And back to what we want to find. We want to find the capacitance. Okay, what is the capacitor? Where is the capacitance? Actually, where is the CL, the load capacitance? Okay, so actually what we're looking at here is something like this. So we have a back-to-back. Okay, something like this. So VDD, ground. So your drain actually is connected to the gate. Okay, M1, M2, M3, and M4. Okay, so you see here, this is a drain. The drain is connected to the gate of the next transistors. Okay, and where is CL? So CL is right there. So this is CL on the output node. So here is your output node. Okay, output is here. Output is here. Okay, so input is there. Here let's call it the load node. The loading node that we are interested to find, because the speed of the first inverter depends on CL. Okay, so CL that we're gonna look at is here. Okay, what is the capacitance? What is the capacitance basically on this line? Okay, so what are the components of the capacitor on that line? So I think it's quite messy. Let's just start again on this one. Okay, so let's get a new one here. So what is the fan out? So the C fan out is actually given. C fan out is CG3 plus CG4. Okay, so CG3 is here. Okay, so this capacitance there. So if you imagine from the top, you have a metal plate, the gate outside, and your bulk or your channel down below. So this is your CG3, and here is your, the smaller one is your CG4. Okay, so CG3, CG4 right there. And if you remember, the CG3 is actually C gate to drain overlap plus C gate to source overlap plus the channel, the gate to channel, and remember, the gate to channel depends on the operating region. The GDO, CGDO, CGSO overlap is constant. It does not depend on the region. But here they say we can just simplify. Basically the capacitance there is you can say C aux W, which is here W, and this is your L. Okay, W times L. Okay, outside capacitance per area times the width times the length, and you have the capacitance on G3, and here is also the same. Okay, so G4 is C aux. Okay, here WP LP, Cox Wn Ln. Okay, and the size given by there, Wn Ln. Okay, so that is your capacitance, the loading, what is called the extrinsic or the fan out capacitance. Okay, the fan out of this, and then you also have the drain capacitance. Okay, here. Okay, so here you have C dB. Okay, the diffusion, C D1 B1, C D2 B2. Okay, C dB1 or C dB2, which is basically a diffusion capacitance. So and here is your and here is your CW, your wire capacitance, and therefore you can then say that your CL is simply CdB1 plus CdB2 plus CW plus C gate 3 plus C gate 4. Okay, so you have the intrinsics. Okay, so here is your intrinsic capacitance, you have your loading capacitance or your extrinsic, and then you have your wire capacitance. Okay, as you can see here, so you have your dB, and you also have your the gate to drain. Okay, the gate to drain. So the gate to drain is here, the small one here. Okay, so here the small one here is your CGD1, and then you have a small, there is CGD2. Okay, okay, so plus CGD1 plus CGD2. Okay, okay, so these are your intrinsic, and then here is your extrinsic. Okay, or the fan out or the load capacitance, and here is your wire, and then you have your total total CL. Okay, total CL on the load line. And here I think we've seen already in the previous notes, slides, we've seen the equations already, quite similar. Okay, so again, it's all about dimensions, it's all about understanding where the capacitors are. Okay, so we can see here that we have the current flow, from the source to the drain. Here is your IDP. Okay, and then you can also have a current flow going down here, okay, from your drain to your source, which is your IDN. Okay, and if we are writing a logic 1, okay, if this transistor is turned on, i.e. if we give a 0 volt here, okay, we give 0 volt on the input, then what happens is we are going to turn on. Okay, so this one's going to be off, this one's going to be turned on, and IDP is going to charge this whole capacitance, as you can see here. Okay, this whole capacitance. Okay, so how fast can we charge it? Depends on the resistance of your PMOS and the capacitance on the load. Okay, so the smaller the capacitance, the smaller the load capacitance, and the smaller the resistance of your PMOS, then the faster we can charge the node. Okay, which means the faster is our circuit. Okay, so let's look at the propagation delay equation. So propagation delay is proportional to the time constant of the network formed by the pull down resistor and the load capacitance. So TPHL, we're looking at high to low. So high to low is we are trying to discharge the value on out to ground. So it's a function of Rn and Cl. So TPHL is ln2 R equation Cl, so it's 0.69 R equation Cl, 0.69 R equation PCL, and then we have our average propagation delay. So to equalize rise and fall time, make the on resistance of the NMOS and PMOS approximately equal. Okay, so what is important here? So CL we've seen already. We know the components. So again, I repeat here, your component is intrinsic. So you have several components in your intrinsic, and then you have the extrinsic, which is your fan out. Is going to where? and then you have your wire. Okay, so CL, we know what it is, we can calculate already. Now the tricky part is how to obtain your R equation. Okay, so what is the resistance? What is the resistance on what is the resistance on the effective resistance of the transistor? Okay, so I think it should be in the next one. Okay, so this is just a simulation values that they show. So these R equation they obtained from simulation, 13 kilo ohm, 31 kilo ohm, using WL, WLN, WLP with some of these parameters, and they get the propagation delay. But we want to analyze how to get our R equation. So to see how then can optimize the delay of gate, expand the R equation in the delay equation. So we have this. Okay, ln2. How we get ln2, if you remember, is the equation to charge and discharge a capacitor. So it's a basic RC charging network. Okay, so 0.69 RC, CL we know. Okay, so R equation. So here they analyze that in the case that VDD is much larger than VTN plus VD set n divided by 2, then we can simplify the high to low propagation delay as this, given by this. Okay, and from here actually you can actually get your R equation, R equation n. Okay, so later on we'll see more examples how we can actually use this equation, but this is one way, okay, of the few ways that we can get the resistance. Okay, so basically if you think of resistance, so R equation n is actually VDD over IDN. Okay, because let's say we are discharging a node like this. Okay, so here is your out. Okay, so what is your R equation n? So it's just your VDD divided by your IDN. Okay, so if you know your current, is IDN, and you know that your node that you want to discharge or you want to charge is VDD, then VDD divided by IDN is you'll get your resistance. Okay, so this is one way, but remember this is a little bit tricky because your IDN, is it constant or not? Okay, so what does IDN? VDD is, you can say, is constant, 2.5 volts, but your IDN can be changed according to the operating region. If it's in cutoff, your IDN is 0 because you have an open circuit. If it's in linear, you have maybe a smaller IDN. If it's in saturation, what is your IDN? If it's in velocity saturation, what is your IDN? Okay, so your IDN is not constant. So if it's not constant, how can we get the R equation? And is R equation, is it constant or not? Okay, so it turns out later we'll see more examples that we can actually approximate R equation based on several values of IDN. Okay, so that's another way of how to get your R equation and approximate the speed of your inverter or your gates. Okay, so later on we'll see more examples on how we can calculate from a circuit, how to calculate your propagation delay using the R equation and NCL. Okay, so as a summary for this chapter, design for performance is very important. As a circuit designer, we always want to be as fast as we can go. Of course, being aware about the power issues as well. So if you go back to our basic equation, the RC charging equation, where TP is equals to 0.69 R equation CL. So how to make it low propagation delay, which is how to make it fast, is to have low CL and low R equation. So basically that's it. So reduce CL. Okay, and know what are the components. Be aware of what are the components of CL. As we've seen, we have the intrinsic, extrinsic, and the wire. So if you are able to understand and understand those parameters and how they impact the speed, Okay, so this is one. Number two, increase the WL ratio. So what happens if we increase the WL ratio is basically we are going to get a higher current. Okay, because remember your ID is proportional to your WL. Okay, so if you have higher WL, higher current, therefore your R equation will be lower because your R is equals to V over I. Okay, so we have a higher current, so your R will drop. Okay, so that's the idea. However, we have to watch out for self-loading. We cannot simply just make our WL as big as possible as we can make. That's not going to work. Okay, we'll see later in the later chapters that how actually transistor sizing is actually an art by itself. There's an art to it on how to make the right sizing, to find the right sizing for the transistor to optimize its performance. Increase VDD. Okay, again we have R equals to VDD over ID. So if we increase the VDD, we are going to increase VDD. Okay, can trade off. Okay, increase VDD can trade off energy forming. Increase VDD above level, you will be more reliably concerned impose a firm upper bound on VDD. Okay, so increasing VDD will increase the okay. So here is if this is constant, so increasing VDD will also increase the I actually, right? Okay, so here actually goes down. Okay, so increasing VDD will increase our current, and current increase will probably be higher than the increase in VDD. Therefore, your total resistance will be lower, and then you have a faster circuit. Okay, so in the next part here, we'll discuss later. We'll discuss in class during our live class session. We'll discuss the exercises and how to solve some of the problem sets in the course. Okay.